This is the fourth lecture in Unit 2. It's titled What Just Happened. It says time is what prevents everything from happening at once, Albert Einstein. So, the first thing we want to do is we want to look at the learning goals. It says students will be able to determine when a time is unavailable for measurement, algebraically generate the last kinematics motion equation, and recognize motion as relative to different reference frames, and use this kinematics motion equation, which is the fourth and final one, A equals Vf squared minus Vi squared divided by 2 delta D. So what we already know that all of the variables of kinematic motion, we know acceleration, final velocity, initial velocity, time, and displacement. You should be able to choose the correct equation given the variables, and that we also learned in the lab that there are instances in where you do not have time as one of your known variables. Okay, we learned that whenever we're looking at situations after the fact, or we don't have a stopwatch available, or it's not an easy situation in which to measure time, there are those sort of situations. We also learned that motion is relative to the observer. So for example, if there are two cars that are traveling at 60 miles per hour in the same direction, to each other they look like they're not moving, but to everybody else they look to be going extremely fast. So we talk about frames of reference. So the first thing I want you to do is sit still completely while you watch the video. Sit still. Now describe your motion. And it's kind of one of those trick questions. People say, well, if I'm sitting still, I'm not moving. Some people will be, well, yes, I'm still breathing, or yes, my eyes are still moving, and that is the case. But the point of this is to look at your frame of reference. Your frame of reference is where you observe motion from. Okay, so for example, most people would say that the figure was motionless in the previous example. But really, it's only motionless relative to you or to the Earth. But in actuality, motion depends on where you are observing the motion from. So for example, if you were sitting perfectly still watching this video and I was observing you from, the moon, you would appear to be going very, very quickly because the Earth travels at incredible speed around the sun. So motion depends on the frame of reference or where the system is being viewed from. Now, unless otherwise stated, it is assumed that all motion is observed from Earth. Frame of reference continued. So here's an example. It says car A is traveling at 20 meters per second west relative to Earth. Car B is traveling 22 meters per second west relative to Earth. From car A's perspective, it appears like car B is traveling 2 meters per second west while car A remains in place. So it's kind of a comparison value. If you're going 60 miles an hour and somebody's kind of creeping up behind you at 65 miles per hour, it appears like they're approaching you very slowly. However, if you turn that around and they're headed in the opposite directions, okay, if you are in a head-on collision, it's extremely dangerous because at that point those velocities add towards one another. And so these cars appear to be going 40 meters per second relative to one another. Okay, another extension of this is the frame of reference. So whenever you're talking about what's called a tailwind or a headwind, whenever you're in a plane and you experience a tailwind is something that can actually speed the plane up. The speed of the plane is measured relative to air, but if the air itself moves like you have with a wind, that actually increases the velocity of the plane. So in this example, we had a plane that was initially traveling south at 150 meters per second. Because there was a tailwind that pushed the car in the same direction, whenever it pushes the plane in the same direction, the plane is actually moving at 160 meters per second. Now, if the same plane experienced a headwind of 10 meters per second, it would actually slow it down to 140 meters per second. So if we look at the first example, it says a people mover, which is like a flat escalator, is moving toward an airport gate at 4 meters per second. You're late for your flight and run at 6 meters per second relative to the ground. If the gate is 500 meters away, how much time do you save by running on the people mover instead of standing on it? So, if we were to look at this as an original question, it says the people mover travels at 4 meters per second for 500 meters. This is not an accelerated motion equation. Because of that, I can use my constant velocity equation, which is V equals D over t. In this case, I have a constant velocity of 4. I'm traveling 500 meters, so I divide it by t. You take this thing right here, you rearrange by multiplying both sides by t. When you do that, you get 4t equals 500. Divide both sides by 4, and you get a t of 500 divided by 4, which is 125 seconds. Now, that's the first part of this particular question. So if I don't run, it'll take me 125 seconds, or a little bit over 2 minutes in order to get to the gate. So now let's do the exact same thing, but let's do it with a new velocity. Whenever I take into account the fact that I run on the people mover, if I run at 6 meters per second relative to the people mover, and the people mover is moving at 4 meters per second, that velocity, so this thing is moving at 4, and I'm running on top of it at 6, those velocities are going to add together and give me a velocity of 10 meters per second. Which now when I run those 500 meters divided by time, I can solve the exact same way, and when I do that, I get a time of 50 seconds. So the only difference between these two situations is the fact that I'm moving relative to the people mover. And if you look at that, it actually cuts down my time quite a bit. Where it takes me 125 seconds standing still, it only takes me 50 seconds if I run, saving me 75 seconds, or almost a whole minute. Now that doesn't seem like a lot, but if you're running late for a particular gate, it makes sense to run. It's an example. It says a Boeing 747 takes off at 7:04 p.m. from the George Bush Intercontinental Airport in Houston and heads towards San Antonio. It says the plane experiences a 15 meter per second wind for the entire duration of the trip. Now it says that it's a round trip, which means it's going to start here and it's going to travel this way, and then it's going to travel back. Now, it says assuming that everything goes as planned, will the plane land in Houston on time? Now, in this particular case, the question is saying it's leaving from George Bush, going to San Antonio, and flying back. Now, you have to justify your answer with the clear method. Now, if you think about it, is it going to land in San Antonio on time? And the answer is yes. In fact, it'll be early. The reason why is it has that additional tailwind that allows it to push the plane, and it'll actually arrive in San Antonio a little bit early. Now, assuming that everything goes as planned, they get off early, they load early, and they take off early, they will turn around and go back. But now at this point, they're running into a headwind. But because they were so early on the initial trip, all the time they saved will be used in the fact that they're going to have a slower trip going from San Antonio to Houston. But those two things will actually negate each other out. This will cancel out with this, and you will actually end up being on time as long as the winds don't change. Now, this is a particularly difficult question. It says a car is stuck behind a large truck carrying bales of hay on a single-lane highway in East Texas. The truck is traveling at 45 miles per hour on a 70-mile-per-hour road. The law allows you to pass the truck using the other lane, but you have to pass the truck within 100 meters or risk hitting a construction crew up ahead. You hit 70 miles per hour just as you reach the back end of the truck. Will you pass the 20-meter truck before hitting the construction crew 100 meters ahead? So, if you were to look at this, relative to the truck, these are your two velocities. The truck is traveling at 45 miles per hour. The car is traveling at 70 miles per hour. So the car, relative to the truck, is traveling at 25 miles per hour. Now that velocity, I can then calculate. You would have to convert, and you should be familiar with how to convert from miles per hour to meters per second. If you need a refresher, you would say that 25 miles per hour, and you'd say in 1 hour, there are 3,600 seconds, and in 1 mile, there are 1,600 meters. If you were to multiply that out, you end up with a velocity of about 11.1 meters per second. Now, that's the velocity of the car as it's trying to pass the truck. So you also have, in this case, the distance of the truck, or the length of the truck that the car has to go. And that's a distance of 20 meters. And some people get tripped up here because they say, well, wait a second, it's 100 meters that you actually have. And yes, you do have 100 meters before you hit the crew, but remember, you're just talking about the car and the truck at this point. So this car has to get 20 meters around this truck before it can pass. And we want to figure out how long that's going to take. Once again, this car is traveling at a constant velocity whenever it hits this point. So you'd solve for the time, and the time in this particular case would be 20 divided by our velocity, which when we put in the calculator, ends up being about 1.8 seconds. Okay, so it takes 1.8 seconds for this car to get around the truck. So now we need to see if that's reasonable as far as this construction crew up ahead. Okay, so I'm going to go ahead and erase this and clear up a little space. And we have 1.8 seconds. That's our target goal time. 1.8 seconds. Okay, so now if we look at it just in terms of the car and the construction crew is traveling or has a distance of 100 meters. And once again, the car is traveling at a constant velocity. But relative to the construction crew, the car is not traveling at the 25 miles per hour we looked at earlier. It's traveling at a constant 70 miles per hour. Now, you should be familiar with converting 70 miles per hour into meters per second. When you do that, you get 31 meters per second. Now, if you were to then go ahead and plug this in, it's actually 31.1. If you were to plug it into V equals D over T, you would get 31.1 equals 100 divided by T. Multiply both sides by T, divide both sides by 31.1. And when you do that, you actually get a time of 3.21 seconds. Now, since the time that it takes to get to the construction crew is less than the time that it takes to pass the truck, this would actually be an acceptable passage at this point. Now, it's also kind of tight. It's about 1.4 seconds of leeway on either side, and then we're talking about very high speed. So it is a dangerous and risky pass, but it would work. In the What Just Happened PBL, we learned that there are situations which time cannot be retroactively measured. And one of those examples was a car crash. And so we learned that there was an equation that related the variables of acceleration and displacement and velocity without time. And that's the first one that we've had without time, and it was the equation A equals VF squared minus VI squared divided by 2 delta D. And so that is the equation without time, and here's where the algebraic here's where the formula comes from. If you look, we have our original two kinematics motion equations. You have the one for delta D equals 1/2 VF plus VI times T. This is the original average velocity calculation, and this is the one that defines acceleration. Now, if you want to set this up, you can actually solve both for T. So that's relatively easy, algebraically speaking. You set 1 equal to T, and then you substitute in. Partly the most difficult part for some people is in this right here. Whenever you do that, you have to FOIL from Algebra 2. So you'd FOIL and do first, inner, outer, last, and it simplifies, and you get this version of the equation that you see here. Now, we're not going to ask you to prove this particular equation or develop your own equation, but just know that all the equations that we've talked about come from the connection between these two particular variables and solving for one variable that I want to isolate or one variable that I want to get rid of or something along those lines. So this is the equation, and it's A equals VF squared minus VI squared divided by 2 delta D. It's used in a situation in which you don't have time. Those are all the kinematics variables that we've already talked about. Displacements, change in position, velocity. You should be familiar with all those terms, especially all of those units by now. So let's work through some example problems using this equation. It says a car accelerates from rest, so we're going to underline that, to 85 meters per second and 400 meters. What is the acceleration of the car? So I know that I'm trying to solve for the acceleration, so I'm going to go ahead and just write that off the bat, say A equals question mark. I know that I have an initial velocity of 0 because of the term rest. I know that I have a final velocity of 85 meters per second. Now, some people may be saying, well, how do you know that it's not 85 meters per second as your initial velocity? And the reason why it says from rest to this. So you're starting at 1 and going to the next one. And then finally, you have a displacement of 400 meters. And it says, what is the acceleration of the car? You're going to use the equation A equals VF squared minus VI squared divided by 2 delta D. And there's no algebraic rearrangement necessary, so you can just plug your numbers in. You could say A equals 85 squared minus 0 squared over, we're going to call it 800. Now, I would highly advise you to go ahead and multiply this out before you do calculations with your calculator. A lot of times people will make a mistake and they'll divide by 2 times 400, and if you do that without the right number of parentheses, you'll actually get an incorrect answer. So make sure you're careful with the order of operation there. Now when you do this in your calculator, you get an answer of about 9.03 meters per second square. And the next question says, what is the maximum height of a baton twirler, of a baton thrown upward at 20 meters per second will it reach? So once again, we look, I'm trying to find the maximum height. I know that it's thrown upward at 20 meters per second. So I can say, well, I'm trying to solve for height, and that's got to be displacement. I know I have an initial velocity of 20 meters per second, and that looks like it's about it. Now remember, there are some key information that we have in the fact that it's thrown upward or vertically. I do know that whenever I have something that's moving vertically, the acceleration is always 9.8 meters per second squared to the negative because it's on Earth. So I know that right away. The second thing that I know based on this particular problem is when you throw something up at its maximum height before it starts to come back down, its velocity instantaneously comes to 0 before it starts moving back down. So I know that the final velocity is 0. Now if you look at that, I can now use the equation that we've been talking about. A equals Vf squared minus Vi squared divided by 2 delta D. Now at this point you could plug in, or you could solve algebraically first. I'm going to go ahead and solve algebraically first because it's a little bit easier for me. I'm going to multiply both sides by delta D. When I do that, delta D crosses out here, and I've got A delta D equals Vf squared minus Vi squared divided by 2. I'm going to divide both sides by A, and I end up with delta D equals Vf squared minus Vi squared divided by 2A. At this point I can plug it into my equation, and I can say delta D is equal to 0 squared minus 20 squared divided by negative 19.6. Once again, I would recommend that you multiply the denominator and go ahead and write that down so you don't make a mistake with order of operation. So now you have minus 0 minus 20 squared is going to be a minus 400. Okay, I went ahead and wrote that out so you can see it as minus 400 divided by minus 19.6. You know it's going to be a positive answer. Those negative signs are going to cancel each other out. And when you do this, you end up getting a displacement or a distance of 20.4 meters. In this example, it says a driver sees a cat in the middle of the road 15 meters ahead and immediately slams on the brakes. The driver has a known reaction time of 0.34 seconds and was initially traveling at 12 meters per second with a maximum deceleration of 5 meters per second. It says, will the driver stop in time? So let's look at the acceleration part of this to begin with. I'm given an initial velocity of 12 meters per second. I'm given an acceleration of negative 5 meters per second squared. Now the reason why I know it's negative 5 meters per second is because it says deceleration. That means it's got to be slowing down. The next thing that I know is I'm trying to solve for the displacement because I want to see if it's going to hit this cat. Now in order to not hit the cat, it has to come to a stop before 15 meters. So I know that the final velocity has to be 0. Okay, so now I can use the equation A equals Vf squared minus Vi squared divided by 2 delta D. I'm going to go ahead and plug my numbers in this time. Last time I solved algebraically, this time I'll plug in. We'll say negative 5 equals 0 squared minus 12 squared divided by 2 delta D. Okay, you see it's a very similar situation to what we had last time. We can simplify this. We can say negative 5 equals negative 144 divided by 2 delta D. Now remember, you've got to get delta D to the top because you have to deal with it in a numerator, not a denominator. So you multiply both sides by delta D, and in doing so that crosses out, and now you have minus 5D delta D equals minus 144 divided by 2. Okay, at this point you could simplify it and you could say negative 72. Now you divide both sides by negative 5, and when you divide both sides by negative 5, 72 divided by negative 5, you end up getting a 14.4 meters. So at first glance we say, well, it takes 14.4 meters for him to decelerate. The cat's 15 meters ahead. He's going to narrowly miss the cat, but the driver has a known reaction time of 0.34 seconds. What that means is that the driver travels at a constant velocity of 12 meters per second for 0.34 seconds before he recognizes the cat is in the way. When that occurs, you can solve for the displacement he travels during his reaction time, and you would say v equals delta d over t, and you would solve 12 equals delta d over 0.34. You would multiply both sides by 0.34, and when you do that, 12 times 0.34 is 4.08 meters. So he travels an additional 4.08 meters while he's reacting to the fact that there's a cat in the road. Because of that, and the time for the distance required for deceleration, he actually travels 18.5 meters whenever you take into account some significant figures. And unfortunately, the cat doesn't have time to get out of the way.